then what I would be interested in terms of describing the magnetic field is this distance, or the distance to some point there, let me call it R, out here. So I want to determine, or rather I can easily determine the magnetic field due to, at this point, due to the uninterrupted current density that I'm subtracting this bit from, right? So I pretend that I've got the entire wire, and I calculate the magnetic field from that. And that magnetic field, let's say if the current is into the wire, actually, I probably want to do this, current out, normally out, will give me a magnetic field that circulates. So, okay, like circulates like so, right? And then when I subtract this bit here, right, I'm going to actually add this, so I'm going to end up now with that. I'm going to subtract a magnetic field that looks like that, right? And I can write down what those fields are going to look like. The magnetic field from the big guy, right, is some constant. There's a C and all that other stuff in there. I'll just call it some constant, right? Times the distance R from the center, this is going to grow, and the magnetic field is going to circulate. So it's going to be R Z. R cross Z. And my magnitude looks like R, so all right. That's what my magnetic field looks like. That will give me the circulation. I don't know if it gives me circulation in the right direction, but that's my circulation, right? The magnetic field due to the small guy is, okay, let me call that R prime, where I measure R prime from the center of this guy, cross Z. Get a minus sign because the current's in the opposite direction. So the total magnetic field in that region is some constant times R minus R prime cross Z. Okay? But you're going to hate this. Some of you are really going to hate this, right? R prime is equal to R minus H. Okay. Done. 3 lines, if you wanted to find those things. I saw some homeworks in here that took a page. You did a really good job. Isn't that beautiful?
Yes. That's how I do.
Who did it? Wait, but that was after I told you.
Yes.
Yeah.
That doesn't count.
Oh, and I guess I should say that those of you who came to the homework help session yesterday had some help. And if he's timely about it, Eli has been posting the homework help sessions online. So if you can't make it to the homework help session, you can still look at what hints I'm giving to people.
When YouTube is not
How
being...
many of you did more work than you needed to?
Given that that was the amount of work we needed to.
Yeah.
Then yes.
When YouTube isn't dumb, I try and get them up that night.
Okay. now things get messy.
Oh, goodness.
Oh, goody, goody, come.
I'm going to talk about materials with magnetic fields, combination of materials and magnetic fields. And I'm going to take a few minutes to talk about what kind of response materials have to magnetic fields and why. But I actually consider that to be more in the purview of a quantum mechanics course or maybe quantum physics 2 than an electromagnetics course. So I'm just going to tell you, how you think about it. And then assuming that you've had a great quantum physics 1 and quantum physics 2 course, then you can just go back and study these things in a little bit more detail. Or assuming that you just have a good book, then you can go back and take a little bit more careful look at this. So I think what I want to do is maybe start out by reminding you of what we know so far. Where are we? And that would be the electrostatic Maxwell's equations we know so far, and the electrostatic boundary conditions that we know so far. And I hope that I'll be able to put those over here, oh, and maybe over there, on the two ends of the board, and then we'll leave those up. Right? So how about, yeah, probably right here, electrostatic. What do we know? We know that we can deduce the electric field from Coulomb's law, and the electric field obeys some relationships, right? I really want to remind you, because in a couple of classes, maybe next class, I'm going to be breaking some of these things that I'm telling you about here. That this is electromagnetic statics. That is no time-dependent anything here. So the problem we were talking about there, that was a steady current which existed forever, right? As soon as we start changing things with respect to time, then things actually get complicated. The other way of writing this that can be useful to us is that you got d, let's call it L over R. Closed path is equal to 0. Electric field is the static electric field that comes from Coulomb's law is a conservative vector field, conservative force. What else do we know? We know that the divergence of the electric field is 4 pi times the charge density, where that's the total charge density in a problem. And we can define a displacement field. D is equal to epsilon E. As long as I'm writing these things down and I don't actually have to do anything with them, I'll be honest about this. I'll tell you that that's a tensor. Right? We didn't use the tensor properties before, but it is. Right? And then that tells us that the divergence of D is 4 pi rho free. And you should not use the curl of D. This divergence relationship here is also related. I won't go further down, I'll stay up here. Maybe I should have done this here. Don't worry, I'm not changing too much. That gives me that. The two things are equivalent, right? This one tells me that the flux of the electric field through a surface is equal to constant, some constant, yeah, well, there we go, 4 pi rho dV, enclosed volume, charge. enclosed by that volume. And then because those two things are true then that means that the electric field can be represented, because that is true. Actually, let me write this down. That tells me that the electric field can be represented as the gradient of something, and the way that we define that something means we get a minus sign. Right? And because of that, then this gives us, does this have mathematical meaning?
It
does.
implies and it is implied by.
Equivalency.
Is that okay?
Logically equivalent to.
I don't know whether I'm mathematically correct here.
Logically
You're
equivalent.
about to write.
But I'm just going to write
Yeah, double arrow.
del
No.
squared by E.
If it's an equal with two arrows on the other side, it means
4
logically
pi
equivalent to.
rho.
If it's just one bar in the middle, it's.
Only works in conjunction with previous statement.
Different order.
Okay.
It's
So
an
probably I
only-
can't do this. Is that what you're saying?
No, you can. Well,
It's fine.
Yeah.
I mean,
We got it.
physics. Physics.
There's a new symbol.
What's the symbol for
No.
because mathematic effects?
Okay, no. I'm sorry. I will make a new symbol. It's Bersant's logic.
We call it the Persanzian.
You could call it the Persanzian, and when you use it, it is Persane.
I
And
like that.
if you really get into it, then it's Persanity. Okay.
it's time like this that make me really love my job.
Good.
This will be going up tonight for anyone
I'm probably
interested.
going to erase these, right? But I'll do some more. In static fields, the divergence of the magnetic field is equal to 0. And that implies the same relationship that I have over there, except that now I can write that flux of the magnetic field through a closed surface is 0. Right? Gauss's law for magnetism. Right? Curl of B is 4 pi over C times the current density, which tells me this, that the magnetic field integrated along a path is equal to the integral over a open surface bounded by that path of 4 pi over C J dot K. And then we know that B is equal to curl of A. And we can write down expressions to deduce, well, we can deduce B from this, all right? But we can write down a relationship that would give us A, which, barring constants, I don't have it written down here, is just going to look like this. Integral over a volume, J of R prime over R minus R prime d prime. Okay, so if we know the current, then we can solve that problem, right?
It's 1 over C out front.
1 over C here, here.
Yeah. It's when you sub in J in terms of B, you should get a
Yeah.
1 or pi.
Okay, so that's pretty much what we know so far. And I had introduced another quantity over here, which in which we said that the D field is equal, we define this new thing, the displacement field, is epsilon E, which is also equal to E plus 4 pi P, I think. I didn't write that down in my notes, but we created this displacement field, which can sometimes make calculations easier. But the thing that actually gives rise to the forces on particles is going to be the electric field. And this thing here is the polarization field of a material. So we added the material in when we do this, right? Now we're in magnetics, and we want to add the material in, right? So I'm going to define a new quantity, which we'll call the magnetization. And the magnetization is, I think I'll write it this way. It's the density of dipoles that's in a material times, actually I need to, density of dipoles per unit volume times the magnetization per dipole. Right? And what we want to do is figure out first I'll just talk about how materials respond to the presence of a magnetic field and how, what that magnetization might look like. But I'll comment that maybe the most common observation of magnetization is for a material that has a built-in stored magnetization that doesn't go away very rapidly with time, magnets, right? And that you don't commonly find materials that have a stored electric field in them. It's very hard to store an electric field in a material and have it stay there. The material's called an electret, but so they exist, but they were, let's say, discovered very late, whereas magnets have been known for a very long time. And because magnets were known for a very long time, the language sort of got turned around with respect to the B field and the magnetization. Right? Magnetization was thought of as being the fundamental thing, and the B field was the result. Right? But the B field is the thing that interacts with moving particles to give us forces. And the B field is the thing that's derived from special relativity and Coulomb's law, right? Okay.
And then there's an H somewhere in there, isn't there? An H field.
I'm going to come to H later on, right?
Ah.
But it might make sense, actually, that we might have some other quantity, like I defined the D field over there. I might have some other field that we can construe as being due to the free currents. So the B field is due to dipoles, which we're going to consider to be bound currents, just like we had bound charge and free charge. And so the B field comes from dipoles, quadrupoles, whatever poles we've got in the problem, and the motion of free charge. The H field comes from the motion of free charge only, okay, not the dipoles in the problem. So it turns out that H is equal to D minus, I think.
It's just a reflection of the other one, essentially.
There's a minus sign.
Yeah, there's minus.
And because I'm not sure of that, I will put that.
That is it.
I'm really liking those symbols.
Equation, equation 45, that's it.
Was it correct? Okay, and I can remove.
You don't need a Persantian. No, that's not the same.
That actually wouldn't be a Persantian.
No, that wouldn't.
We have to think of a name for something which is an equal sign with a Persans brand on it.
Yeah, it's a per sequel sign.
A per sequel.
Right, okay. You guys can work on that.
It's a per-sequel sign.
All right. So, let's see, yeah, I'll do this first, and then I'll talk about mechanisms for magnetization of materials. So, I want to talk about, did I do that right? Yes, I did. I'm going to rewrite this in a slightly different way, which is that the magnetization of a material, right, is 1 over some volume, right? So it would be magnetization times the volume, right? Is the sum over in that volume all the magnetic moments, and it's a vector sum. So this is actually what I would do is take every dipole in the material and say what's the average dipole moment in a particular direction, and then add them all up, right? So this one has an average hidden in it. That one does not. The average is explicit. So I'll write it like that.
1 over delta V?
Some volume. 1 over some volume. Does that deserve a peek? No. And then we want to find out what the magnetic potential is from that collection of dipoles. And one really nice thing is that the magnetic potential, you can apply superposition to it. So if you have the magnetic potential from one thing and another thing, you can just add those together, given that you've taken track of all the kept track of all the distances, and you add them as vectors, right? So the final magnetic potential of a dipole is this. That's the dipole. It's just that. And we can get the magnetic field from that just by taking the curl of that, right? And I'll leave it like that. So if I want to find the magnetic field, the magnetic potential, due to a collection of dipoles, I've got to add up all of those dipoles. So I can say that the magnetic field due to some volume, some infinitesimal volume of space, right? When I've got now magnetization in my material, is going to be minus the magnetization per unit volume of that volume. Okay. And so that's why I wanted my delta E over here. Okay. I'll make it infinitesimal now. And write it like that. If I want to, and I do, I can do that. I just flip the signs in here. And I got rid of my minus sign. That was nice. Yeah. Which can be written like this. the total vector potential then is just the integral. I can save myself some trouble. Is the integral over the prime volume. So wherever the dipoles are, they give rise to a small bit of magnetic potential, and I just add up all the magnetic potentials. So in some sense, we're done right now, okay? If I know the magnetization as a function of position, I can do that integral, right? But it turns out that there are some more meaningful ways to look at that. The arithmetic is there. You can just do the arithmetic. But there's a nice way to break this apart, right? I can view this as one part of the curl of the product of m times 1 over r. Right? So I'm going to rewrite this integral this way. It's the integral of curl of m plus, I have to make sure I have the right number of parentheses. Yeah, plus 1 over r minus r prime. That. I just used a chain rule in there in order to do that, okay? But this now, I see that I've got the curl of something measured over, integrated over a volume, right? And if we remember Stokes' theorem, then we know that we can transform that into an integral over a surface. So let me do that. Part of it I have to keep, and the other part is the straight curl. Right? So that vector potential becomes the integral over the surface, a surface that contains all these magnetizations, right? Of plus an integral over the volume where the dipoles are.
Isn't there a cross product sign between the ds prime and the other thing?
No. It's going to be a vector. I think I'm okay. Oh, I don't like what's an Ohanian there. I will see whether mine comes out better than his. I will drop pi's and 4's and c's, but I think that in the end, mine will be easier to interpret than his. So I hope I didn't make a mistake. So this is still a volume integral, and I still have a curl in there. Okay? But I transformed that curl into a surface integral. Okay? This is maybe what you're looking for.
He has a curl sign there. Did he define his S to be in the direction of the surface?
I like mine. All right? So that's, I'm going to claim, and then we can check it later, is the vector potential due to a material that's magnetized, where the magnetization can depend upon position.